Okay, today we started talking about the frequency regulation and control section. In this section, we are going to cover the modeling of the speed governing system of a synchronous generator, which is usually considered as the primary frequency control. And then we move to automatic generation control, which is usually considered as a secondary frequency control for the region. And we also cover some other frequency controls not done by generator, such as the load. You can do load shedding to mitigate the frequency declines, which is called end frequency load shedding. So the materials will be from one chapter or from Kunder's book. We'll also use some materials, examples, and also homework problem from a chapter of Sadek's book. I highly recommend everybody read through the chapter 4 on April tutorial. So that one can give you a better perspective from the industry. So this figure shows the diagram of voltage and frequency controls for a synchronous generator. So far, we have learned how to model the synchronous generators, which is basically the circle with G. And we have in our modeling, we have treat the field winding can provide the constant field voltage or constant field current, which is denoted by IFD, which is the field current. And in the synchronous generator modeling, we don't consider change on the field current. But here we're going to discuss how that can influence the voltage of the generator. So that will be covered by next session in voltage control. And another loop will be how to change the power input to the generator. So this is going to change either Tm, which is the mechanical torque, or maybe the Pm, which is the mechanical power, which has about the same value in per unit. This is done by another loop, which is frequency control loop. This session will cover the bottom loop, frequency control loop. And the next session will cover the top loop. So those two control loops are called local frequency control, FFC loop, or automatic voltage regulator loop, AVR loop. The frequency control loop can also control real power, and the voltage control loop will control the ready power. Those two loops are usually configured for specific steady-state conditions, which means if a steady condition change, their settings may also need to be updated for the best performance. So their purpose is now to ensure the stability of the voltage or frequency. So their purpose is mainly to mitigate or reduce the variation of a frequency or voltage near the equilibrium point or near the steady condition. So when you design those two control loops for the steady conditions, they only are able to reduce or mitigate the very little variation from the steady state. If you have a large disturbance, they definitely will still can help to reduce the variation, but you have to rely on some other control to ensure the voltage stability or frequency stability or transient stability. The coupling between the two control loops are usually ignored because the excitation system is to control the voltage and the field current of field voltage. Their time constant is much smaller than the time constant of the turbine or inertia of the generator. So usually the control loop of a frequency fall into the transient time frame. If you consider maybe the fluctuation of frequency, the control loop can take even longer then maybe a tenth of a second to bring the frequency back. So the bottom control loop is much slower than the top control loop. But the top control loop doesn't involve any mechanical part. So the time constant is very small. It basically done by a power electronics or digital controller. So time constant is very small. So the control loop with voltage control usually fall into the time frame of subtransient dynamic. So it's reasonable to decouple those control loops when we discuss a voltage control or frequency control individually. Okay, we don't have to worry about the other loop. But if you want to simulate stability of the system under large disturbance, those two control loops will interact. So eventually, you have to consider the control, the effects of both loops to judge the stability. So a better practice will be to model the voltage control loop and frequency control loop accurately and to do the time domain simulation. Okay, so the time domain simulation will cover both subtransient and transient dynamic. And finally, the loss of stability can be caused by either the frequency loop or caused by the voltage loop, which means it can be caused by either IT power or reactive power. Okay, but for this session, we don't consider the voltage control loop, and we only focus on small disturbance that can change frequency. Okay, something about the frequency control. The frequency of a power system depends on the balance of a real power or active power. Okay, any change in real power primarily affects system frequency. While reactive power is less sensitive to frequency variations and mainly depend on change in voltage and magnitude. So there could be some controller they said this is like frequency controller or active power controller, real power controller. They basically mean the same thing. Okay, because by changing the frequency, you will change the active power. By regulating active power, you are going to change the frequency. Okay, so here we don't differentiate the frequency control and from a active power control. Similarly, later in the voltage control section, we'll cover both voltage controller and a reactive power controller in the same session. Frequency for a power system is a common factor throughout the entire system. Any change anywhere in real power on the system will eventually be reflected across the entire system by the frequency. So you may have a very large interconnected power grid and many generators. A disturbance like tripping, maybe one generator will first influence the speed of a neighboring generator, and gradually will propagate to the entire system. So if you simulate the behavior of all generators, you will see the speed. Some speed will change first, and some speed will change later. But eventually, when the system get to the new steady state condition or the equilibrium, they all have about the same frequency. So that make a frequency to be very efficient index or indicator for wide area control. Okay, so there are so many wide area controllers. They focus on frequency because they can measure frequency anywhere. They don't have to build up like a communication system to collect data from sensor at different locations. They just place a sensor locally to measure the frequency. Like for instance, if you have any chance to visit a control room, the control room, there's a display to show you the system frequency. So that system frequency may be taken from just locally, right, from the local data. Yeah, that may not be close to the location of the fault, but eventually that value will reflect there's the system frequency. Okay, so if your system is really huge, you can have multiple locations, but you really don't need to have very accurate communication system because eventually your entire system shares the same frequency. If I have an interconnected system with multiple regions and each region has number of generators, in order to control the frequency better, in other words, you want to control the real power and the flows better, you need to have control in each area. So you need to control the active power and frequency of each generator, or maybe at least some generator in each area. Even you don't have control of every single generator, but you want to have some control in each area. So that area in the US is called balancing authority. Okay, remembering we talked about balancing authority. Balancing authority is the smallest region where you need to keep the real-time balance of active and reactive power. So for each balancing authority, you need to have at least one generator which can do the frequency control, which means they can have regulation, governor, and you need to connect it to the automatic generation control system. Also, you need to control the tie line. So later when we move to some examples on the frequency control for interconnected system, we will try to control both the frequency deviation at some generators and also some tie line flow. So we need to control both. The control of generation frequency is commonly referred to as a load frequency control. Basically, low frequency control consider two levels of control. The first level is at the generator level, is called the primary frequency control, done by speed governing system of each generator. And the second level is automatic generation control, AGC, for interconnected system, or at least for one area of the system. Any question? Next, let's talk about the frequency deviations. Under normal conditions, the frequency in a large interconnected power system, such as Eastern connection, Western connection, Texas interconnection, typically varies by approximately 30 millihertz from the scheduled value. So if the scheduled value is 60 hertz, the frequency changing from 59.97 to 60.03 hertz is considered normal condition. Okay, you don't need to do any control within that narrow range. But outside of that range, you need to take some regulation action. And there are abnormal events, such as the loss of a large generator unit. The frequency can have very large deviation. Okay, and this figure is from the April tutorial. The first chart cover much wider range from 56 hertz to 64 hertz. So using color to indicate abnormal versus normal condition. So normal condition is typically considered in the first chart, it just rigorously speaking, just the green line. Okay, but you can extend it a little bit to the blue region. The blue region is maybe starting from maybe 59.5 to 60.506. So basically just give you half hertz variation from the center 60 hertz. That is considered somehow like a nominal frequency. But literally speaking, the normal frequency really means the very close to 60 hertz. So if you zoom in, the blue region in the first chart and to get the second chart, you see that the green region only cover about maybe 10 to 20 millihertz, right? So there's two green lines. There's a two green line here. So if the frequency go outside of those two limits, then the governor need to take some action to respond to that. Within those two limits, the governor doesn't need to respond, even if you have frequency deviation. That is done by setting the what is called the dead band for the governor, because you don't want the governor to respond so frequently, right? That's not good to the generator. You want the governor only respond to some necessary events, like frequency go above 20 millihertz. So 20 millihertz or 30 millihertz is usually the setup for the dead band of most of the governor. Okay, so if we cannot maintain within the blue region and we somehow move to towards the red area, for instance, when the frequency change by 1.5 hertz, go to above 61.5 hertz. So there will be a protection which will trip the generator because the generator is operating under over frequency condition. Similarly, if it's too low, near maybe 59.102. So there will be an under frequency load shedding to try to stop the decline of the frequency. And if it's too low, go to like 58.5, right? So there will be under frequency generator trip. So if the frequency go to a very high or very low, the generator will be damaged, or some other related equipment will be damaged. Those two figures give you how the real frequency variation is. So in the first figure, it shows the variation of frequency under normal conditions. So you see the frequency is never stay exactly at 60 hertz. It will always fluctuating, right? So that's usually considered like ambient data. So if you have synchro phasors or PMUs to measure frequencies, you will see such oscillations. Such oscillations are usually caused by the change of the load. The second chart indicates what the abnormal frequency look like. So if something happened, like for this case, okay, so time is actually increasing from in this direction. No, I think it's wrong. The opposite. Yeah, the time is go up. Yeah. So at this moment, something happened, and the frequency dropped from 60 hertz to the lowest frequency reached around like 59.9192 hertz. Okay, and then quickly recovered back to around 60 hertz. If we compare this rectangular area, this scope versus the top one, so that green box indicate the exactly same area of the bottom one. Okay, so which means if something happened in the top figure, that frequency change will look like this one. So it's significantly different from a normal frequency variation for disturbance. So you can easily tell when the something happened, some disturbance or contingency happened on the system. What is the impact of abnormal frequency to generator? So the first, they can damage the power system equipment, such as generators, and can also damage the turbine blades of steam turbine generator. And for such generator, they can only withstand a very limited amount of off-frequency operation over their lifetime. For example, if right now system is at 58 hertz temporarily, a typical steam turbine can operate under load for 10 minutes over its lifetime. So if the frequency stay at 58 hertz, this turbine will be over after 10 minutes. But if it temporarily, like a few seconds, it might still create some permanent damage, but it can continue to operate. But when such damage accumulated for a long time, it will eventually damage, which is like when you drive a car. If you drive a highway, that's usually fine. But if you drive local and suddenly there's the road is not paved, if you keep driving that road every day, so eventually your car will get damaged sooner. So they chart indicates, so if you can maintain the frequency within half hertz, positive or negative 0.5 hertz, usually it's fine. You can ignore the damage to most of the turbine generator. But if it's over half hertz, so you will move to this yellow area. So for this yellow area, the most optimal case is you can operate this generator for 50 minutes of the lifetime. Okay, so if you have even higher or lower frequency, eventually the time will become smaller and smaller. If I really low frequency, like 56 hertz, they only take 0.01 minute, a few seconds, which is enough to damage this blade turbine generator forever. So that's why you need to have protection. to respond to the low frequency, very low, very high frequency instantaneously. Okay, the protection can be set up with very, very short time, like a few cycles. All right, next we can talk about how to model the turbine governor. And in the previous session, all the modeling work has been done for that the right box. We model the generator starting from the equivalent circuit, and we introduce power transformation to have a D-axis and Q-axis circuit, and gradually derive the differential equations and simplify the model. The simplest model is just use swing equation to model how the mechanical torque changing from how the electric torque changing from mechanical torque can cause a change on the speed and angle. That's what swing equation is talking about. But now we are going to model how the turbine will determine the mechanical power and how the speed will be feedback through the governor and to influence the opening on the valve and the output of turbine. So we talk about that the low frequency control loop. We'll focus on the blue and green boxes here. Here in the modeling we can either use torque or power, and so power is equal to the product of the speed and the torque. So if the speed is at 60 Hertz, the nominal frequency, then when we calculate per unit value for power and torque, they are same. Okay, and here in this section, we can treat power and the torque be equal in per unit value. Why? Because as we just saw, the frequency can only operate within like a half Hertz variation. Half Hertz divided by 60 is about less than 1%. Which means even if we consider the normal frequency, which is at the blue or even the green area, right? So the green area has 0.01 Hertz, 10 millihertz divided by 60 Hertz. So that can be ignored, that variation. So which means for normal condition here, which is the first chart, not the second one, not the second one. Second one can be covered later by stability session, but here we only just consider the very small variation of frequency. So in this case, it's safe. We can consider the frequency in this section is always very close to 60 Hertz. Then that makes torque be equal to power in per unit. Does that make sense? All right, so under the rated condition, the mechanical power is equal to electric power, and which is all equal to be maybe I call it P0, indicate the system condition. And this one is actually also same at the torque, the rated torque. And that is also equal to mechanical torque and electric torque. But if we consider a very small change, delta omega r, but which is much smaller than the synchronous frequency. So this omega r will be a 1 plus delta omega r. So when for this case, we consider the difference between the mechanical power and electric power, which is equal to the difference between their variation under the same frequency change. Because the power is equal to the speed multiplied by the torque, so we can easily get this equation. But because delta omega r is much smaller than 1, so the first parenthesis will be about 1. So this one will basically just 1. Okay, which means in this section we can treat the change in the power be exactly same as change of the torque, which can be calculated by the difference between change of the torque. So in this entire section, so in any equation, wherever you want to utilize the swing equation to represent how the frequency can change, although the original swing equation can take this one or that one, but eventually you can use anyone here. They basically treat it the same, depending on which one is more convenient for you to do the analysis. So we don't differentiate those 4 items. They are basically treated exactly the same in this section. Okay, so now we can, we need to gradually modeling this entire system. We start from this generator model. So why do we want to model generator? Because although we have discussed generator modeling for many lectures, we never discussed about the modeling for generator together with load, right? We have, the previous session is about the load modeling, and the session before is a generator modeling. We never talk about how to model the generator load together, because here, why do we want to do the frequency control? Because there's a change in the load, okay? So this entire system is to do the load frequency control. We do need to consider both generator frequency and the load. So that's why we need to bring them together. This is our swing equation. And so when you write down swing equations, you need to be clear what unit you're going to take here. Like for instance, here we assume all the torque and power are in per unit, and even omega is in per unit. Okay, so if omega here is not in per unit, the first equation is going to have omega 0, and the bottom equation has no omega 0. So if you see another set of swing equation like this one, you will realize immediately, okay, delta omega r here will take a unit radian per second. If you don't see the omega 0 in the first equation on the denominator, which means omega r will be per unit value. And h is the inertial constant, which has unit time, a unit of time in seconds. So how do we model the load? The load from here will be the electric power going to that load. But we also need to add a second item. So if there's any change on the load on this equipment, so electric power will change. But we also need to add another atom, which is a linear function of frequency deviation. Why do we add this atom? Because from the load modeling session, we know some load can be frequency dependent. Okay, so it's safer to consider the frequency dependency to the load. So this is the frequency independent part, which is, for example, ZP load, or can be exponential load. And they need to be multiplied by a factor which is near 1. And the difference will be linearly changed with the frequency deviation. Okay, the factor will be a KPF. So usually KPY will take a value maybe 1 to 2, right? So you can find that the table from a previous session. So this is the load model. So based on this frequency dependent load model, we can have the 2 items. The first item is frequency independent, or not sensitive to frequency. The second is sensitive to frequency. So where does the second item come from? It can be caused by any like frequency dependent load, or it can be some damping effect of the generator. So if your generator has some like damper winding, which can help provide some damping torque or damping power, so that one can be modeled here by this item. So the second item is an integrated effect of both frequency dependent load and also maybe the damping effect on the generator. Both type of quantities can be modeled by a linear function changing with a frequency deviation. So if the swing equation has per unit value on both sides, so which means the delta omega r here is a per unit frequency, then D should not have any unit. So D's meaning will be percentage change in load for every 1% change of frequency. That's what the D means, which means for the power and the frequency, you both take a per unit value, okay? Then you divide the load change, per unit load change by the per unit frequency change. That will give you the D value. And D has no unit. It's just a number. So now we can generate the either differential equation or block diagram considering both generator and load. From the swing equation, we can have this equation. So if we apply Laplace transform on both sides, and we also add the frequency dependent item here. So because those total give you the change on the electric power, right? So next one, you can move the items about the delta omega r to the left hand side. Then you can immediately get this block diagram. Okay, this tells so the change on the mechanical power due to the turbine and the change on the load, which is not sensitive to frequency. Their difference will determine how the frequency will change of the generator, and through this first order component. Okay, so this is in this block. Remembering when we introduce the swing equation, I emphasize that H is not time constant. Do you remember what 2H means? What double H means? Double H means some time, but how long is that time? Yeah. So you just you start this unit from a standstill until the rated speed using the rated power. That's how much time it takes. That's 2H. Okay. So which means H has the unit of second or time, but it doesn't mean time constant. So now you understand why it's not time constant, because what is time constant really depends on the D. So this is first order system. You can definitely change this first order system to some standard form like TS plus 1. So now if we can change it to this form, the K will be the gain, and the T or tau here will be the time constant. That will be the true time constant. That determined by both H and D. So on the generator zone, you cannot determine time constant. You have to know what load or what system is connected to. Okay, so D, because D will depend on the system, doesn't exactly only depend on the generator. Only although D can include some damping effect from generator, but majority part will be from a frequency sensitive load. Any question? Okay, so now let's see how the frequency deviation can be if we don't have any low frequency control. So now let's just assume the H has value 5 seconds, which means 2H of the time it takes to speed up from the standstill condition until the rated speed will be 10 seconds using the rated power. That's 2H value, 10 seconds. And the D here is a 0.75, which means the load will change by 0.75% if there's a change, 1% change in frequency. Okay, that's D value. So now we consider the load will decrease by 0.01 per unit, which is about like 1%. If the load is 100 megawatt, so here we'll only just decrease the load by 1 megawatt. So let's see what happened on this generator. So this is the model on the transfer function from the load change to the frequency change. So if we translate this one into the standard first order system with a K and the T, so here we can calculate the K will be 1 over D, which is 1.33. T will be M divided by D, which is 13.33 seconds. So time constant is about like 13 seconds. So that means what does the time constant mean? If the time constant is 13.33 seconds, which means if any change on the system, that the system will take 13.33 seconds to change, to decay for majority of the initial change, right? But decay to about only 37%, which means majority of variation is done, it's over. That's what this time constant means, which means for this generator take a very long time to eventually to reduce or mitigate the majority of the change on the load. So let's do some calculation. So now the load decreased by 0.01 per unit. After Laplace transform, that will be a negative 0.01 over S. The speed deviation from that transfer function will be the transfer function multiplied by the input, the step change. Okay, so if you plug in all the values, and so you can decompose this product into a two component. So next step, to get the time response, you need to utilize inverse Laplace transform to each component. So I assume everybody know how to do it. So the answer will be, there are two items. The first item is exponential function with a negative exponent regarding that time constant. The second is just a constant value. Okay, so if we plug in all the numbers, so it will have a time function for the first item, and second will be just a constant value. So if we draw the trajectory of a frequency deviation in time domain, so the frequency deviation will increase from 0 gradually until the final frequency deviation will be 0.0133 per unit. Okay, because frequency or generator speed here is a state variable. It cannot change instantaneously. So even you add step function, step change on the load, the frequency will take some time eventually to go to the steady state condition. So by about 13.33 seconds, it will change. That make a majority of change towards the final condition. Okay, so this value will be the final frequency deviation. So because the unit is per unit, so 0.01 is about like 1% of the nominal frequency. Okay, so that sounds pretty small. But if we translate that value into the unit of hertz, so that is 0.8 hertz. So it's too bad, right? If you compare this one to the what we define for normal frequency, right? The 0.8 hertz is already maybe start tripping some protection. But think about it, we only just change the load by 1% of the unit. This example tells, so it's very critical to have low frequency control. We want to reduce this value. We don't want that 1% of load will cause maybe 0.8 or even close to 1 hertz change on the frequency, right? That's too bad. How can we reduce this value? We need speed governor. So next we are going to model that everything this green box, the governor, and which will be responsive to the speed and will change the valve opening and eventually will influence the mechanical torque or power. Okay, so this is a picture of a speed governor from the 19th century. This is a picture I took this picture a few years ago in the museum. But if you look at the picture, you cannot imagine that one was made by like more than 100 years ago. Okay, but this principle is almost exactly the same as today's governor, especially if we're still using like a centrifugal governor for steam engine. But definitely this is not for the power plant. This is for some other like steam engine. So most interesting part will be this one. So you have two metal ball, and each one will have a certain weight. right? So their distance can be bigger or smaller, depending on the revolution speed. So you see that long wheel, large wheel that will rotate, will revolve, and that speed will translate to this speed. So will be translate to the distance between the two flying waves. So if that wheel has very high speed, which means the two flying waves will carry high kinetic energy. Okay, so their distance will be bigger. So when the distance become bigger, so it will move this part. They can move this pole up and down. Then that one will influence the opening of some valve. Okay, so if that distance is too large, so that will influence the valve opening and eventually can make the speed to decrease. To give you a better picture, this one is more detailed principle of this centrifugal governor system. So you see here, it is the speed. So if the speed increase, that will make the two balls, the two flying waves, more separate because they have higher kinetic energy. They have because of centrifugal force, they will push the two flying waves apart. Okay, so what happened? And this point will go down, and this point will go down, and this point go down, and this point go down. So there will be more high pressure oil enter this tank to push this one up, and this valve will become smaller. That's the design of this centrifugal governing system more than 100 years ago. So if you have any chance to work at power plant to be involved in the modeling of like governing or turbine system, the most accurate governing turbine system we have maybe 200 to 400 components. So each component using a linear component to model time constant. For instance, here, this is already very simplified figure. Like any arrow, right? When I start showing how the speed increase, that will cause the separation of the flying waves, and that flying wave will cause the decrease of point B and point C. So any part can be modeled by some linear system at a certain order. So when you connect all the transfer function together, that can give you maybe 200 or 300 order transfer function. Okay, then for that function, you can draw the bow diagram. For some study, if you research or studies focusing on this optimization of this the turbine or generator power plant, you can keep this accurate model. But if you want to provide a model to engineer for power system stability study, they don't need this 200 or 300 order system. They can use a bow diagram and to somehow simplify the model, similar to the frequency response, right? When we draw the bow diagram based on how many time constants you want to consider, you can use the bow diagram to fit the transfer function and only give you maybe simplified model. Because one of my past PhD student did intern at a system operator, so her job was actually to reduce this $200 model to eventually maybe 2nd order, 3rd order model. Okay, and by that, along with her internship, and we did a very interesting study because at that time there's somebody developing the fractional order system, which means you either take this 200 order system, that's accurate model, okay, or you just reduce the number. But once you reduce the order, the model will not accurate. But another idea is you can use a fractional order. The order will not be order 2. It can be 2.1, 2.2, 2.3. So there are some methodology have to define how to draw the bow diagram of maybe 2.3 order system. So why I say 2.3 really means in the transfer function, you're going to see some like 2.3, the fractional order model. Okay, but when you draw the ball diagram of the fractional order system, that can match very well with the 200 order system. So, which means you can only use much fewer parameters to categorize the original turbine or governing system. Yeah, that's only just for convenience of categorizing the model. But you also use fractional order system, that's another challenging problem. You still need to translate that back to 100, 200 order system for accurate representation. Okay, but that's something related to this. But I just want to give you an idea on the actual turbine or governing system can be very complex. But in the stability study, usually we can reduce this order to maybe 2, 3, or 4, very low order system. So the most critical part to model speed governing system is actually based on this block. We need to introduce the speed governing characteristic. If there's no governor, okay, there's no such input. Okay, so we already used one example to show if there's a change on the load, and the frequency can change significantly. But now we can introduce the governor. The governor will measure the frequency deviation, and through certain gain, which is this 1 over R, will translate, provide some suggestion on how to vary the opening of valve and to influence the mechanical power. Then this signal will indicate how much you're going to change the valve opening. So we'll take another transfer function to finally to really change the valve. So the governor is basically just provide this the negative feedback control loop. The key idea of this governor speed governor control system is basically just a proportional control. It cannot mitigate the speed deviation. It can only just reduce the speed deviation. So it does not eliminate the speed deviation due to the load increase. Because in order to have the control signal, non-zero control signal, so this speed deviation cannot be 0. It relies on the non-zero speed deviation to provide the control signal. Okay, so which means it only can reduce the speed deviation, and by going through the gain, a very large gain, it can just translate back to how much you're going to change the valve. But the change on the valve cannot eliminate the speed deviation. This is the drawback of proportional control. Usually this R has to be very small because 1 over R will be the gain. You want to translate the small deviation to some change on the power, right? So gain should be large enough. Usually R will take the value from maybe 5% to 6%. That will make the gain to be about 20. So the delta omega R divided by the capital R will be the how much you're going to change on the power. So finally, the signal going to the turbine will be first the change due to the speed deviation, and second will be change from the reference. So this reference will indicate how much you want the generator to output. So that can be from the schedule value. If you do a economic dispatch, you want to dispatch this generator to provide 100 megawatt at this point. So that P ref will be 100 megawatt. But if later, if you want to increase this value, the delta P ref will be positive, or you want to decrease, that will be negative. So the feedback and the change on the setting point together will determine how much you want to change the opening on the valve and turbine. In order to finally change the valve, it have to go through some time constant. Here we just call it a tau g. Okay. So if we draw the this figure, how for generator controlled by the governor, how the frequency can change with power, output power. So it will be a negative line, negative slope line. So which means when the power increase, the load increase, the frequency will drop following this slope. And the slope R here, the slope R here is defined by how much frequency change divided by the change on the load. So if you consider a triangle, the Y will be the frequency division, X will be a change on the power. All right, let's see how the speed governor can influence the frequency after some maybe change on the load. So here X is the load of the generator and Y is the frequency of the system. So if the load is completely frequency insensitive load, which is the red line, which means the load has no room to negotiate. It has to be exactly 1,000 megawatt, no matter what frequency it operates. So it will be this vertical straight line. So if the system has some frequency sensitive load, which will be this blue line. The blue line, which means, so if right now the frequency is exactly 60 hertz, okay, so the load will be 1,000 megawatt. If the system frequency drop to 59.4 hertz, decrease by 1%, and the load will decrease to 970 megawatt. If you have an even lower frequency, the load will be even lower because the frequency sensitive load. Especially for IT power, usually that KPF is positive, right? That's why I make the slope along this blue line to be always positive. Remember that caused by KPF. For IT power, usually this is positive. So if the load has both frequency sensitive component and frequency insensitive component, eventually that will become the green line. Will be something in the middle. So here, let's just assume we just use a straight line to approximate the total the load characteristic with D equal to 2. D equal to 2 means for 1% of the frequency change, okay, the load change will be 2%. So if the frequency is exactly 60 hertz, the load will be 1,000. If frequency drop by 1% to 59.4 hertz, the load now become 980 megawatt. So that would be the green line. So what if we add the governor? Okay, if we add the governor pushes the generator operating point only move along this orange straight line with negative slope, which is negative R. Okay, because one over R is again, R is very small, like 0.05. So which means this slope will be like negative 0.05, for instance. So it can be very flat, very small slope. So it will intersect with the load characteristic at that point. So if we are operating a system with none of the load to be frequency dependent, which will be the red straight line. So right now the load decreased by 2%. So the new operating point will be this one. The frequency will increase. So if I have a generator with governor connected to 1,000 megawatt load, and that 1,000 megawatt load suddenly decreased by 20, the frequency will increase to that new operating point. So not too much, right? So compared to 1%, that change may be just 0.5, 0.4%. It's very small. So that is guaranteed by this very small slope with the governor. But now, if you load is not completely a frequency incentive, it also has a incentive part, which is the green line. So what happened is when you decrease load by 20 megawatt, so that 20 megawatt is measured at 60 hertz. Okay, it's not measured by new frequency, but because new frequency we haven't known yet. We don't know. We just know right now. For example, there's a 1,000 megawatt load, and 2% of load. The frequency dependent load is evenly distributed everywhere. But right now, based on the 60 hertz, I know 2% of load is gone. It's just disconnected. So what is the new frequency? So we need to move the green line, shift the green line to the left by moving by 2%, which will be this line. So new point will be this black dot. So compare that to the right dot. This new black dot will be lower, which means it has even smaller frequency deviation. So the final frequency deviation is determined by both the governor speed characteristic, which is R, and also D. Both D and R tell what the final frequency deviation is. Okay. So you either has very large D, which means you have more frequency dependent component, or you have very small R. They both will contribute to decrease the frequency deviation. We'll talk about that in more detail later when we go to the equation. But now you just keep in mind. So the D, larger D or smaller R, they both can contribute to reducing the frequency deviation. Okay, so you didn't think about the early example, right? The load change by 1%. Remember, we assume like decrease by 1%. If there's no R, but only have D, to make up that 1%, that delta omega has to be large enough, which is 0.8 hertz. But now we add a second item, which is 1 over R. R is a small value. So that can make delta omega be much smaller if 1 over R is much bigger. That's key idea on or the contribution of the governor to mitigate the frequency deviation. All right, so to summarize what we observed from this example, so if D increase, which means that there's more frequency dependent load, then the green slope will be smaller, and delta F will be smaller. If R decrease, which means a stronger load frequency control feedback, okay, or a bigger gain with the governor, then the orange slope will be smaller, and the delta F will be smaller. Okay, any question? All right, so next we want to model the turbine. Okay, from the opening of the valve translated to the change on the mechanical power. So we assume this change cannot take instantaneously, right? You still take some time. And as I said, so if you model that turbine system, how the speed deviation going through governor, going to change the valve opening, and finally influence mechanical power, that can be a $200 system. But here we don't have to consider that compliance system. We can use very simplified model, which is accurate enough for stability study. A prime mover for single generator is the source of mechanical power. So it can be from a combustion turbine, if it's a natural gas power plant, or it can be from the hydro, if it's a hydro power plant. So the model of the turbine relates the change in the mechanical power output, which is the delta PM, to change in the gate or valve opening of delta PV. Okay, delta PV, here we also use capital P because here we consider everything in per unit. So which means that the PV, which is how much the valve is open or closed, that value can be translated into how much power if we consider they have roughly linear relationship. So that's why we use P everywhere in this entire control loop. To model this system for turbine, we can usually the total time will take from 0.2 second to 2 seconds. It will take less than a couple of seconds to really change the mechanical power of torque. If you open the valve and use timer, and after a number of components, finally it will take this time to really change the power and torque. So now we can draw the entire closed loop control by considering each component as a first order system. So here we ignore all the nonlinear function, all nonlinear, maybe limit or deadband. So we just only model the time cost or time constant for each part. And that this will be the simplified model to talk about this entire control loop. And which is good for this section, because in this section, we only focus on small disturbance. But later, when we want to study the transient stability or other stability, we may need to gradually add more nonlinear component to make this loop be more complex and more accurate. But now you can, if you want to draw the transfer function, so this will be the transfer function. Does everyone know how to write down the transfer function if I show this block? Okay. So simply speaking, so if you have any transfer function like this one, so this is, we can call it f. And this, yeah, so usually we call, yeah, this one should, usually we call it g, which stand for the open loop transfer function, and f maybe stand for the feedback. If it's a negative feedback, and this x and this y. So what is the transfer function of y over x? So there will be, what is the numerator? The numerator will be g, right? Assume it is s function. And what is the denominator? 1 plus gf, right? So if you use this formula, you can write down any transfer function. So here, y can be anything. Here, you can. It doesn't have to be whatever on the right, right? You can use any one to be the y. Like for instance, here I use delta omega r to be the y, and negative delta pl to be the x. So here this is y, here is x. But if you want to write another transfer function on how the reference value will influence the speed, you need to count all the 3 blocks on the top to be g, and only the bottom one to be the f, right? But now if you when you write this one, so the g will be only this one, right? F will be the multiplication of everything here. Then you do some simplification, you will get this one. All right, so check your notes if you don't remember how to do such one, because you're going to do some homework about this block diagram. All right, so let's do some very simple analysis based on this transfer function on how the frequency will change by load. So the system had 2 inputs. The top one will be changed on the load, and the life will be changed on the setting point. So where is that setting point? I forgot to show you here by this figure. The setting point is here. So in this figure, there's a motor turn screw, which means you actually can use that motor to move that screw up and down. If you move it down, that actually push all the point A, B, C, D, E, everything down, which allow the 2 flying ways more separate. So which means the entire system will operate at higher speed. If you move that screw up, that will make the entire system operate at lower speed. So this will be the input, okay? Although the value is not, it's just the position of that screw, but it doesn't tell the power, but that one will influence the power. You can translate to how much power you want this generator to output. So now we consider a step change. So the steady state frequency will be, to calculate the steady state value, that will be the from that transfer function and multiply by s, and then let s be close to 0. So you estimate steady state frequency. So you don't have to do the inverse Laplace transform. You can use this principle to estimate the steady state value. Okay, so you just multiply the delta omega r s by s, then let s be 0. So which means this is 0, this is 0. They're all 0. So eventually steady state frequency just this one. If you really want to see how the generator respond to this step change, so this will be from a time domain simulation. So the speed will decline to have some what is called like a nadir frequency or speed nadir, which is the minimal speed frequency, then will go up. So finally we'll reach the steady state deviation. Do you remember if we don't have speed governor, how does the frequency change? So that will be like something like this one, right? It won't go up. It will stay at very large deviation, maybe 0.8 hertz for that example. But because now we have governor, the governor will through the negative feedback, it will bring the frequency back. But the frequency deviation is never 0. So this is not 0. So there's always some gap. So the speed deviation will be translated into how much mechanical power is going to change. So you see, this is the lower point of frequency, and that is the highest point of the mechanical power. So there's some delay. So that delay time is about the time total time constant translated from the governor all the way, from the speed deviation all the way through those blocks. Right, that will take a few second delay. It's not instantaneous change on the mechanical power. So how about we have a multiple generator together supporting the same load? So this equation is still correct, but R here has to be a total regulation. By total regulation, which means we need to somehow integrate all the characteristics together, okay? Because 1 over R is really the gain. Okay, so if you have a multiple generator, each one will contribute some frequency deviation. So when you add them together, which is like when you connect many parallel branches in the circuit, so each branch will carry some current. The more branches, you have more current. So we need to take this formula, which is a parallel connection. We just treat R, each one as some resistor of the parallel circuit. So the total R will be a parallel connection of all the R. So which means if you decrease any R, the equivalent R will decrease. So in the power system, every generator has speed governor. If you make any governor to be most sensitive, the entire system will be most sensitive to frequency. So this is like in the parallel circuit, if you make any resistance to be smaller, okay, the current will be bigger, right? That one will influence the total equivalent resistance or impedance. Okay, the next question will be, it seems that the smaller R, the better. Is that true? Definitely, when asked this question, the answer means it's not true, right? It will, if you have any ideas on the stability of the proportional controller, if you use proportional controller, usually you increase the gain, that will help to give you a better steady state condition, but it will increase the dynamics. And if the gain is too large, then eventually the system can become unstable. Okay, it will have very large oscillation. So I will leave that one for next lecture. So next lecture we'll use one example to give some value and to study what range of R we need to use to design this power plant. Yes. No, that band is just a value, but within which you don't need to. The governor, it seems the governor doesn't exist at all. The dead band is like this one, right? Yeah.
Slide 5, the green shaded region.
Yes. Yeah. Let me see. Which is like this one. If you're familiar with such component. So when the speed deviation goes through this component, it need to follow this curve. And this H will be maybe 30 milliseconds, 30 millihertz. So within 30 millihertz, it doesn't change at all. Only when beyond 30 millihertz, it can start change and can influence this one. Yeah, the control design. Yeah. Maybe to answer that question, I would see there can be both physical dead band, depending on what governor turbine you have, or there can be intentional dead band. Yeah, it can be both. Because the dead band, some design of the dead band may be made by the generator manufacturer. Your generator has a very expensive equipment that need to be protected, which means you definitely don't want to make it too responsive and to give more risk of damage. And actually, it doesn't have to. So later, when we talk about automatic generation control, we don't really need to have every generator to be very sensitive. We need at least one generator which can mitigate. Maybe eventually there are only few generators, they help to bring the frequency back to 60 hertz. So all the governor with that band, they can mitigate the frequency deviation until maybe tens of a millihertz, and then you can use AGC to bring the frequency eventually back to 60 hertz. Okay, all right.